kick off this part 2 video from the series, I wanted to introduce a third application, which comes from the excellent book Mathematical Statistics with Resampling in R, and you can find a link to the home site for this textbook, which has this data set as well. Now, this data set basically shows the amount of beer and the number of hot wings consumed by a bunch of customers at a Minneapolis pub on a given night. So beer is measured in fluid ounces and hot wings is just numbered in how many wings did they chow down. So the reason I wanted to introduce this data set is because it kind of shows and gives a little bit of intuition about why we need something more than just a best fitting line, and why it makes sense to talk a little bit about these y observations, our dependent observations as random variables, in fact. So you can notice for this data set that it's sort of discrete in the sense of like hot wings can only be integers. And you'll notice that for any specific example, like for example, for all the customers who ate 6 hot wings, there's sort of a distribution of possible beer amounts that those customers could have had, right? And more customers, we would probably get more here, but this was only in 12-ounce increments, right? So the least squares line, you'll notice what it kind of does is it tries to average out those and pass through somewhat of a mean for each of these different values. So really what I'm saying here is that for each value of x, we have a mean line which, right, gives y, a predicted value of y as a function of x, but then we have plus some random error here. And really, it's that which in the end gives us the response variable y. So thinking of y in this way gives rise to the simple linear model, right? And just to restate what we did on the last slide, but with typing instead of my messy ass handwriting. So the simple linear model is going to assume that our dependent variable yi is a linear function of x. So think of this as the signal, or that least squares line that we saw before. Actually, we don't know if it's a least squares line, but it is a linear model at least, plus a noise term. And in the simple linear model, we assume that those noise terms are IID, right? So they're independent. So for each y, we get an independent noise, and that they're normal with a standard deviation sigma. And it's the same sigma for all x. And that actually is one of my favorite words in statistics, which is homoscedasticity, which I don't even remember how to spell it, but it's a cool word, homoscedasticity, right? Now, once we've kind of formulated things in this way, we can actually get estimates on beta naught and beta 1 as parameters using maximum likelihood estimation. Do you see why? If not, think about what this model is saying, right? This model is saying that y is a random variable. This is just some constant, right? So y is a constant plus a normal random variable. And when you have a constant plus a normal random variable, well, that's just a normal random variable with a shifted mean. So in other words, all of this up here implies that y itself is normal, but with a mean that depends on x and the standard deviation sigma, right, that comes into play. And once you know this, you also know, well, it has a PDF given by the usual thing, 1 over square root of 2 pi sigma, e to the negative yi, minus its mean, right, which is beta naught plus beta 1 xi squared over 2 sigma squared. So notice I have a PDF which depends now on 3 parameters, right? The 3 parameters are beta naught, beta 1, and sigma, so I can talk about the MLEs for those parameters. It's actually a fairly simple calculation. So rewriting our PDF from the previous slide as a likelihood function now, we can simplify this, and I'm going to use proportionality here to get rid of the square root of 2 pi stuff because it's not going to make a difference, right? So we're going to have sigma to the negative n, and then we're going to have e to the negative 1 over 2 sigma squared times the sum of the yi minus beta naught minus beta 1 xi. And I keep forgetting the xi's, those i's in these videos, but we'll add them back in. So taking log of both sides of this expression, right, yields negative n log sigma minus 1 over 2 sigma squared times the sum of the yi minus beta naught minus beta 1 xi squared. And then there's actually going to be plus a constant because we used, that proportionality there. But what's interesting to note here is that this term, okay, right? This term right here is exactly the least squares thing that we were trying to minimize before, right? This is like our yi minus yi hat squared. Okay. So, and this term up front here doesn't depend on beta naught and beta 1. So when we differentiate this with respect to beta naught and beta 1, okay, and I encourage you to check this on your own, we end up getting the exact same system of equations for beta naught and beta 1 that we did when we took a least squares perspective of this problem. And at this point, I'll quote one of my friends from graduate school said his professor at Berkeley always would say, the creator is benevolent when something worked out this well in math. So I will quote that as well here and say the creator is benevolent. We get the exact same system of equations for beta naught and beta 1, which means the MLEs for beta naught and beta 1 are the same as the least squares solutions from the last set of videos. So that means we only have one more parameter left, which is sigma. And I will encourage you to take a moment to look back at the last slide. In fact, I'll flip back for you for a moment here and allow you to pause the video, rewrite this expression, take its derivative with respect to sigma. Okay. But what you'll end up getting is negative n over sigma minus, remember there was a sigma cubed, there's a sigma squared there, so we're going to get a minus 1 over sigma squared times the sum of the yi, minus beta naught minus beta 1 xi squared. There's actually, becomes a plus because we're differentiating a negative exponent here. And when we set this equal to 0 and solve for sigma, we'll end up getting sigma hat squared is 1 over n times the sum of yi. We're going to get beta naught minus beta 1x, but of course then we need to plug in the values for beta naught and beta 1, which minimize the other two partial derivatives. So we'll end up getting beta naught hat minus beta 1 hat xi squared here for sigma. Right. So great, we've got three formulas. And notice here that the sigma hat squared is essentially, okay, once again, you could think of this as a yi minus a predicted yi, right? This whole part right here is a prediction. I wanted to take a moment to talk about the sigma hat squared a little bit more and what it means in terms of partitioning errors and sums of squares for regression models. Now, if you look at the picture on the left, which shows our toy data along with that best fitting line, y hat equals 1.4 plus 0.8x, right? We could look at the differences between each point, the vertical distances between each point and the corresponding points on this line. So these distances here, what they're measuring are the actual values minus the predicted values for y. And we call those differences residuals, okay, and denote them by E sub I. Now, why do we introduce the term residuals instead of errors and yet still denote them as E sub I for errors, for the ith errors? I don't know, but that's the way it's done. Now, using this notation, we could come back to sigma hat squared and we can realize that these right here are just E sub i's. And therefore, what sigma hat squared is doing is it's measuring the average squared error for our linear equation. And in the last video, we called that sum of squared errors SSR. Sometimes it's also called SSE. Sometimes people switch this up and say RSS or ESS. It's just a matter of preference, and hopefully you can keep those straight if you're in such situations. But this quantity in of itself is not the best measure of fit because the y's themselves have a natural variability, right? They're spread out along the y-axis in some way, okay? And what we really want to know is how much of that variability can be explained by the linear model and how much is left unexplained by this linear relationship here. What I mean geometrically is if we measure the vertical distance of each point to the line y bar equals 3, okay? So measuring that vertical distance now, we can note that this distance can be decomposed as the residual plus another term here, which is the difference of yi hat minus y bar. Okay. So the total variability, which is often called SST, is measured by the sum of squared differences yi minus y bar squared. That's the sum of the lengths of those black lines squared. Okay. And the individual differences can be decomposed as a residual plus a variability in predicted values themselves. Now we know that it's not true in general that I can just square this and square both sides on the right. Okay. That just doesn't work. But it turns out in this scenario that if I add a sum on both sides of this equation, I do indeed get an equality here. And the reasons for this kind of deal with orthogonality of vectors, and there's a little bit of linear algebra involved, so we're not going to get into that here, but I do encourage you to think about that if you've had Math 75 or another Introduction to Linear Algebra course. Right? So if you look at this expression a little bit more detail, we can see that this first term here, that's our total variability in the y's. This one here is our residual variability. This one is sometimes called the sum of squares for the model, okay, or the sum of squares of the treatment. And you could think of this as the part of the variance that is explained by the model itself. Now, the R-squared statistic, which you may have heard quoted in regression studies before, is typically stated as the proportion of variance, okay, the proportion of variance explained by a linear relationship with x. So the proportion of variance in y explained by a linear relationship with x. And given these sum of squares here, we can represent that in two equivalent ways as SSM over SST. So what part of this total variation comes from the second term here? Or 1 minus SSR over SST, which is usually how it's computed, 1 minus the unexplained variation. We're going to compute this for both the coronavirus data and our toy example in a moment in R, but just a couple comments here. Note that this quantity itself is always between 0 and 1. Now, the closer it is to 0, what does that mean? The closer it is to 0, if it's really close to 0, that means that most of SST shows up here in this error. So that means that our predictions are not very close to the actual values, and hence our little linear model is shit, right? So R squared close to 0 means your linear model is shit. And an R squared value closer to 1 means that most of the variance in the y's is explained by your model, and therefore you have found a really good, strong linear model. Although there are, of course, other things to take into account, which we'll get into in later videos. Tacking on the code for computing R squared to our previous code is just 3 lines, basically. First, we need to compute the total sum of squares as the deviations of y from their mean squared, so the sum of the squared deviations of y from its mean. Then we need to look at the sum of squared residuals as the deviations of the y's from their predicted values, so y minus b0 plus b1x, sum of those squared. And then R squared is 1 minus the ratio of those two quantities. And in this case, we end up with a value of 0.64, which means that the x's in our case, whatever they are in this toy application, explain about 64% of the variability in the y's. Right? Now, whether or not that's statistically significant is a question we'll examine in the next video. For our coronavirus situation, if we look at R squared for our log model, right? So we're computing the sum of squared total as the square deviations of, remember, log deaths from their mean and SSR as log deaths from their predicted values, then in this situation, we end up with a much higher R squared of about 0.985, which means that dates explain about 98.5% of the variability in total coronavirus deaths. And that makes sense given how well our model actually fit this data in the first place.